Hi. In the previous video, I briefly explained the IR spectroscopy. How does the IR radiation interact with the different molecules, and how does this interaction can be used to interpret or to find what are the different functional groups that exist in a certain compound. And then we talked about the different factors that affect the wave number, the intensity, and the shape of the signals. In this video, we will talk about the practical steps that should be used in order to read an IR spectrum, and how can we read and identify the different functional groups using an IR spectrum. So in an IR spectrum, there are two main regions. There is a diagnostic region and there is the fingerprint region. So anything which is between 400 and 1500 is called the fingerprint region. Usually the single bonds will appear in this region. And then anything which is between 1500 and 4000 centimeter minus 1 will be in the diagnostic region. The fingerprint region cannot be used to extract too much information about the structure of the compound. That's why we will be mainly focusing on the diagnostic region, because this one has less peaks and it can be easily used to identify the different types of bonds that exist in a certain compound. But why do we call this a fingerprint region, and why do we call this a diagnostic region? Let's look at those two spectra here. Both spectra correspond to an alcohol, but the first one is 2-butanol and the second one is isopropanol or 2-propanol. Now if you look at the this region, which is the diagnostic region, you can see that they are almost the same for both compounds. However, if you look at the fingerprint region, which is this one here and this one here, you can see that each compound has a different fingerprint region, and that's why we call it the fingerprint region, because each compound will have its own signals that differ from the others. So this tells us, this region can only tell us if those two compounds are the same or are different. However, we cannot extract too much information from this region because it has so many peaks. However, so in order to be able to identify the different types of functional groups that exist, our main focus will be on this region, which is here, which is the diagnostic region. So we will be mainly focusing on the peaks which exist in this area here, and those will tell us what type of bonds exist in a compound. So let's look at this into more details. So again, starting from 1600 up to 1850, usually the double bonds will appear in this region. So this is the first thing that you have to look at. Usually you have to draw a line at around 1500 and then look at the peaks starting from 1500 up till 1850. If you have any peaks in this region, these usually correspond to a double bond. Now we will tell you later on how to distinguish between, let's say, a carbon-carbon double bond and a carbon-oxygen double bond. Now once you're done with this region, you have to move to another region which is between 2100s and 2300, and this is basically the region where triple bonds appear. Finally, we have to look at the region which is after around, so starting from 3000 centimeter minus 1 and up till almost like 3600 or 700 centimeter minus 1, and this region would be used to determine the different types of XX bonds, as we will see later on. So single bonds will appear below 1500. This is not important for us right now. The double bonds will be mainly between 1600 and 1850, and triple bonds will be between 2100 and 2300. And finally, anything which is bonded to hydrogen, oxygen, nitrogen, or carbon will appear in this region between 2700 and 4000 centimeter minus 1. We will talk about each region in detail. So how can you read an IR spectrum? Let's say I gave you an IR spectrum. How can you read it? How can you identify the different functional groups that exist in a compound using this IR spectrum? Let's start with the first thing you should do, which is you have to draw a line at around 1500. And now look at the signals which are to the left of this line. If you have signals between 1600 and 1850, this is telling you that you have a double bond. These are the numbers. So if you have a ketone or an aldehyde, the numbers will be around 1680 to 750. Now, how can we distinguish between aldehydes and ketones? Usually, an aldehyde will have, and a ketone will just have this peak. A ketone will have, in addition to this peak, a peak which corresponds to this carbon-hydrogen bond between 2750 and 2850. So ketones will only have a peak in this region. Aldehydes will have this peak and another peak which corresponds to the carbon-hydrogen bond in this region. Carbon-carbon double bonds appear between 1600 and 1700. So usually they are at a lower frequency than the carbonyl ones. And again, the CH bond, as we will see in the spectrum, appears between 3000 and 3100 centimeter minus 1. So let's take a look at these spectrums. So for example, this is the first one, which tells us the difference between a carbon-carbon double bond peak and a carbonyl peak. Usually the carbonyl peak will be around 1750, depending on the structure, whereas this one will be around 1680 or 1650. So this one should be at a lower wave number. The other main difference between them is that the carbonyl peak will be always a peak with high intensity, whereas the carbon-carbon double bond peak will be a peak with short intensity, so it will be a short peak. This is, for example, a spectrum of this compound which is here. This is a compound which has a carbonyl group. This is a ketone. That's why, as you can see here, let's say I gave you this spectrum. First of all, draw a line at 1500, and then look at this area, which is, or this region, which is between 1500 and let's say 1850. Okay, so you only have this peak here, which is around 1700 or 1750. This is a peak with high intensity. So this is telling me that this is a compound which has a double bond over it. It has a carbonyl. Now I'm not sure if this is an aldehyde or a ketone. We need more information. Once you're done with this region, you have to look at the other region, which is between which corresponds to the triple bonds between 24 or 2600 and 2800. If there are any peaks here, then this means that there is a triple bond. If there are no peaks, then there is no triple bond. Usually those peaks which appear around before 3000, between 2800 and 23,000, are usually, they don't tell us that much, because basically those correspond to any carbon-hydrogen bond. And since all organic compounds will have carbon-hydrogen bond, then you will always see peaks here in this area. So this area usually doesn't give so much information about it. So we only look at the peaks which are below 2800 and after 3000. Those are the ones which I will be looking at, and most of the time, to identify the different peaks or the different types of bonds that exist in a compound. So again, let's take another look at those two spectra here. This is the difference. Let's say you were given this spectrum. Draw this line at around 1500, and you see this short peak here tells you that this is a carbon-carbon double bond. To make sure that you have a carbon-carbon double bond, look for a small peak at around 3100s. And if this peak exists, this confirms that you have a carbon-carbon double bond, and then you have a hydrogen at this carbon-carbon double bond. Whereas if we have a compound which has a carbonyl, this compound will have a strong peak with high intensity at around 17 or 1800, depending on the structure, and there is nothing else here. Okay, and again, look at this region. See, all of them have peaks in this region. That's why we don't care about those peaks which are before or below 3000. Just look at this region here, this region here, and then anything which is after 3000 centimeters long. So this is the main region this is the main difference between a carbon-carbon double bond and a carbon-oxygen double bond. So the double bonds will appear between 1600 and 1850, and now the triple bonds will appear between 2100 and 2300. If you have a carbon-carbon triple bond, it will be between 2100 to 2200. If you have a carbon-nitrogen bond, it will be between 2200 and 2300. And then if we have a carbon triple bond with a hydrogen, as you will see, it will appear as a small peak at 3300. For example, again, you were given this spectrum. Step number 1, draw this line at 1500. And then look at this region, which is between 1500 and almost 1850. If you have any peaks here, this means that there is a double bond. For example, in this spectrum here, I can see this short peak. So I know that there's a carbon-carbon double bond. And I can see this long peak. So this means that there's a carbon-oxygen double bond. Now, also the second step is look at this region, which is between 2100 and 2300, sometimes 2400, so it depends on the structure. But again, if you have any peaks, and usually those will be short peaks, sometimes they will be long ones, then you have a triple bond. If not, then there is no triple bond. So for example, in this case here, we don't have peaks in this region, so there is no triple bond in this compound. Now, this is an IR spectrum for a compound which has a carbon triple bond. As you can see here, there is this peak which is around 2200 or 2200 almost. It is usually a short peak, and this is telling me that there is a carbon-carbon triple bond. To confirm, there will be another peak. Now in this spectrum, it is a long one, but usually it is a short one, around 3200s, and this is telling me that there is a carbon-hydrogen bond, which was an sp hybridized carbon. For example, if we looked at this spectrum here, let's say I'm analyzing this spectrum. Again, I draw this line at around 1500. See, between 1500 and almost 1800, there is nothing. So we don't have peaks. So there is no double bond in this compound. Now the second step is between 2100 and 24 or 2300. This region here, which is here. We have a peak here. So there is a triple bond. Okay. Now usually it's hard to tell whether it's a triple bond, it is a CC triple bond or CN triple bond. But there are other factors which may tell us whether it is this one or this one. But anyways, whenever you have a peak in this region, then there is a triple bond in your compound. Again, anything which is around 3000 C, this is a CH, so this is not informative, it doesn't tell us anything, and there is nothing in this region. So the only thing which I can tell from this spectrum is that I have a triple bond. And here I have a triple bond, and I also have a hydrogen at a triple bond. Whereas from this spectrum here, I can see that there is a double bond and there is a carbonyl, and that's it. Now, what about the last region, which is the one which shows us the XX bond, XH bond, OH and HCH bond? These usually appear between 2700 and 4000. Now, alkanes, as I said before, they will appear between 2800 or 2900 and 3000. This is, again, a region which doesn't tell us that much, because in each compound, you will have, in most of the compounds, you will have this carbon-hydrogen bond. The second important peak, which is we talked about before, which is after drawing this line at 3000, if you have a small peak, a short peak at 3100s, this is telling you that there is a double bond and there's a hydrogen at this double bond. And if there is a little bit longer peak at around 3300s, this tells you that there is a triple bond and there is a hydrogen at this triple bond. How can we distinguish these bonds from the other ones, like the NH or the OH bond? These usually will appear at higher wave numbers, larger wave numbers, between 3300s and up to 3600 or to 3700, as we will